Okay, so let's look like the imperfection or defect in the atomic and ionic arrangement. So in this chapter, we are going to learn the different types of defects, such as a point defect in the crystal materials, like a vacancy or substitutional or interstitial atoms. Okay, I'll explain this later. And also we're going to discuss about the line defect. The line defect, like the dislocation. Okay, and the dislocations can be classified into two types of dislocations. One is the edge dislocation and the other is the screw dislocation. Okay, and we identify a system for deformation. Okay, it's called the slip system, and the slip system is composed of the slip plane and the slip direction. Okay, and finally, we're gonna explain what the area defect is, which is the grain boundary and the grain size. Okay, so basically we have three types of the imperfection or three types of defect. First is point defect. Okay, point defect. It's point defect. Okay, like vacancy atoms and interstitial atoms and the substitution atoms. And the second defect is called the line defect, which is the dislocations. Okay, and dislocation basically have three types: dislocation, H, screw, and mixed dislocation. Okay, we're gonna discuss this later. And the third types of the imperfection is area defect. Okay, area defect, like a grain boundaries or and the grain size. Okay. Okay, so let's look at the point defect, which are localized, disrupted. Okay, disrupted. Okay, the point defects are localized disruptions in otherwise perfect atom or ionic arrangement in your crystal structure. That means as we insert those point defects, it could be the vacancy or substitutional atoms or interstitial atoms. Okay, the effect of those interruptions from point defect are often fed over the surrounding region. That's mean when you insert an point defect, the lattice surround that point defect will be distorted or will be disrupted. Okay, and this distortion or disruptions will enhance their materials properties. Okay, often these defects are caused by the introduction of other atoms or ions. Okay, we can insert those point defect atoms during the process. When you're manufacturing, we have the manufacturing process, and we can just insert those point defect, just like, for example, like metal alloy, like the steel. Okay, or steel. The point defect atom of steel is carbon atoms, right? Carbon atoms. Also for the semiconductor, we can dope some point defect. We can dope for like for example, we dope the phosphor or sulfur or germanium into the silicon wafer. Okay, that can just modify its property, electrical property. Okay, it can modify the electrical property. Okay, so let's look at this picture. What I already described before is the point defect, different types of point defect. First is the vacancy. Right, it's the vacancy. That's mean the lattice atom or the original atom leave to somewhere. Maybe this atom jump to here, right? And here, the position here is empty. It's empty. Okay, and also we can look at the second type of defects called the second type of point defect is called interstitial defect, interstitial atoms. Right, we insert the different types of atoms into its interstitial site, and the radius, I mean the size of these interstitial atoms could be larger or smaller than the lattice. Okay, it could be larger or smaller than that of those interstitial sites. Okay. Okay, and we also already discussed about these substitution atoms, right? That's mean the lattice atom or the original atom is replaced by a specific substitutional impurity atom. Okay, is that okay? Okay, so let's look at the effects from those point defects. So the first figure shows the vacancy, right? We have a vacancy here. Okay, the lattice atoms move to somewhere, okay, and the vacancy remain, and those remained vacancy will cause the disrupted regionally. Okay, so when these vacancy form, and the local lattice will be distorted. Okay, here will be distorted, okay, or disrupted. Okay, and if we put the interstitial atom into the interstitial site, like here, it could be larger or smaller. Okay, this interstitial atom could be larger or smaller than that of those interstitial sites. Okay, no matter it's larger or smaller, its vicinity or its surroundings, I mean, its surrounding lattice will be disrupted. Okay, will be disrupted. Okay, the same effects of those substitutional atoms like this and this with different atomic radius. Also, their lattice surroundings will be disrupted or distorted. Okay, so the surroundings and the surrounding will be distorted. Lattice surroundings will be distorted or disrupted. Okay, and for the figure E, as the shows, it's called the Frankel defect. That means the lattice atom moved to the interstitial site. Originally is here, right? And it moved to here, or it may move to here or here. Okay, so it's called the Frankel defect. And the figure F represents this called the Schmid defect, which is always happened in ionic materials or ionic bonding. Okay, so for the ionic materials, its charges have to be maintained in neutral. Okay, therefore the vacancy could form for remaining or for remain its neutrality. its neutrality, charge neutrality. Okay, the cation have to equal to the anion, right? Okay. Okay, so let's look at the point defect. Let's look at the point defect. As I already described that, vacancy is when an atom or ion is missing from its normal site in crystal structure. Okay, and the vacancy concentration in materials follows, and it's called Arrhenius type behavior, or the Arrhenius equation. This Arrhenius equation. This. So it is an experimental function. That means this function is derived from an experiment. Okay, so let's define this equation. This is the number of point defect. In this case, it's vacancy, right? The number of vacancy. And this is the number of potential vacant sites, or we can say it's just the lattice point, okay, lattice atom. Okay, and it's an exponential function. It's an exponential function. This Q is activation energy. Activation energy. Okay, and T is temperature in Kelvin. R is a constant. It's a Boltzmann constant. Okay. So what is activation energy? What is activation energy? Give us an example. For any chemical reactions, we need a catalyst. We need a catalyst to facilitate its reaction. Okay, so for example, we have the reactants and we have the product, right? If this reaction, reactions without any catalyst, we need higher energy. We need higher energy to make the chemical reaction occur. Okay, in this case, it's enzyme. Enzyme is the catalyst. We need maybe we need a higher temperature to trigger this chemical reaction. Okay, if we adding some catalyst, adding some enzyme, and this activation energy will be reduced. Originally, we need a higher energy to trigger this chemical reaction. And when we adding some catalyst or enzyme, this activation energy is reduced. That means maybe we don't need so high temperature. Okay, we need some maybe like room temperature or maybe 100 Celsius, such like that. Okay. Okay, so let's look at the equation, the Arrhenius equation. Okay. So this is the number of defect, number of the vacancy, and this n means the number of the potential defect set, or we can say it just each lattice site is potential vacancy site. Okay, and this is the activation energy K in Kelvin. T in Kelvin, and K is the Boltzmann constant. It's a Boltzmann constant. Okay. And this equation is derived from an experiment. Therefore, we can get the QV, we can get the activation energy from an experiment. Therefore, we can measure it. So how to measure it? We can use a method, it's called the differential thermal expansion method. Basically, you have to measure the dimension change in the spaceman and the lattice parameter change. Okay, of course, we have those machine that we can measure this the thermal expansion coefficient. Therefore, like this, we can measure the coefficient of thermal expansion and the temperature K. Okay, and we can get the concentration of vacancy. Have this relation. Okay, this is the dimensional change in the material sample, and this is the lattice parameter change. Okay, and this is a concentration of interstitial site or interstitial concentration. Okay, it can be calculated and it can be estimated. Okay. Okay, therefore we can measure the defect concentration or the vacancy concentration with respect to the temperature in Kelvin. And then we figure out, oh, it's an exponential function. It's an exponential dependence. Okay, it's an exponential dependence. And then we can replot this exponential function into a linear function. How? We just take the nature log and the inverse of temperature. And we can replot this exponential function to a linear function. Okay, a linear function. Okay, and then the slope of this linear function is what? It's a function of activation energy. Okay, so this term is the slope of this linear function. Okay, this is the slope of this linear function. Okay, and K is constant, right? K is constant, therefore we can figure out what's this activation energy is. Okay. Okay, so let's look at some point defect that I already explained before. Okay. Interstitial defect is formed when an extra atom is inserted into the crystal structure at normally unoccupied position. Okay. Although smaller than atoms at interstitial atoms introduce a localized stress. In their vicinity, vicinity, that means the surrounding, and those localized stress often strengthens the material. Okay, as I already mentioned, those point defect will distorted or disrupted the lattice vicinity, and this distortion will cause the pre-stress or the localized stress. This pre-stress will strengthen the material's property. Okay. Okay, so the substitutional defect is introduced when one lattice atoms or ions is replaced by different atoms or ions. Okay, and the substitutional atoms often have different sizes than the regular lattice atoms, disturbing their surroundings. Okay, disturbing because of different size than the regular lattice atom. Therefore, the lattice will be disturbed. Okay, and the substitution atoms often increase the strength of the metallic materials. As I already explained previously, that the point defect has the significant effect on strengthening the materials, especially for metallic materials. Okay, due to the lattice distortion. Okay, due to lattice distortion. Okay, and other point defect like interstitial C is created when the atom identical to lattice atoms occupied the interstitial site. Okay, so what I mentioned in previously like this. Okay, this is the interstitial C. That means the lattice atom, the original atom, is inserted into the interstitial site. Okay. And a Frankel defect is a pair of vacancy and the interstitial site. It's a pair. Okay, when the lattice atom jump to an interstitial site. Okay, so we have the lattice atom here, and it jump to here. We might jump to here. It might jump to here. Okay, we'll jump to those interstitial sites. That's called the Frankel defect. Frankel defect. Okay, and the Schmid defect is unique to ionic materials or ionic bonding. To preserve electrical neutrality in ionic materials. For example, for this material, we have two vacancy, right? Two vacant sites. However, for this whole materials, it is still neutral. It is still neutral. Okay, it must be neutral. Okay, so for example, for these ionic materials, if we want to dope or we want to add in some charge, positive charge, cation 2+, into this crystal materials. Okay, if the neutrality must be remain, the neutrality must be maintained. Therefore, when we add in the extra 2 positive charge ion here, that's mean what? That's mean the 2 positive charge have to remove, okay, to maintain its neutrality. So adding 2+ cation and remove 2 cations. So what's the consequences? What's the result? It is that one vacant site remained, right? One vacant site remained. Okay, and this material is still neutral. It's still neutral. It's still neutral. Okay, so next I'm gonna talk about the line defect, dislocations. Okay, dislocations are line imperfection or line defect. Okay, in the perfect crystal, in an otherwise perfect crystal. They are present in all materials, including ceramics and polymers, and they're especially useful to explaining deformation and strengthening in metallic materials. And basically, there are 3 types of dislocations I already mentioned before. It's screw, edge, and mix. Okay, so when we have a metal rod and we apply a tensile stress, what's going to happen? If we keep applying a load, a tensile load, okay, a tensile load. Okay, inside this metal rod, the face or the crystal will slip. As I mentioned previously, it will slip along the plane. This plane is called the slip plane, which represents the close pack plane. Okay, we apply a tensile force on a metal rod, and inside these materials, the shear force will make the crystal to slip. Okay, and the slip process is following its slip plan, following its close pack plan, following its slip direction, and follow its close pack direction. Okay, to produce the permanent deformation or the plastic deformation. Okay, so let's look at the line defect dislocation. Okay, so the line defects a one-dimensional defect around which atoms are misaligned. So I already mentioned there are three types. Okay, let's focus on the first two types. Okay, first is the edge dislocation. Okay, for edge dislocation, extra half plane of atoms is inserted in a crystal structure, and the B vector perpendicular to the dislocation line. The B is the Burgers vector. Okay, B is the Burgers vector. I'll explain this later. Okay, and the second type of dislocation is the screw dislocation. Okay, a spiral planar ramp resulting from the shear deformation. Okay, the screw dislocations are due to the atomic planes forming a spiral ramp, and the B vector, Burgers vector, is parallel to the dislocation line. Okay, it's parallel to the dislocation line. Okay, let's look at what is the edge and what is the screw dislocations. So the top view, the upper figure shows the edge dislocation, and the bottom one shows the screw dislocation. Okay, and as I already mentioned, for the edge dislocation, an extra plane of atoms form. Okay, when we apply a shear force, it's the shear force. There's one extra plane form. Okay, and this atom move from this point, this original point, to here. This direction is called the Burgers vector. Okay, it's called the Burgers vector. Okay, that's the reason why we mentioned that the Burgers vector is perpendicular to the dislocation line. Okay, this is the Burgers vector. This is the dislocation line. So perpendicular, right? Perpendicular. When crystal materials is when the shear force applied to the crystal materials, the dislocation might occur. Okay, for the edge dislocations, that the Burgers vector is perpendicular to dislocation line. Okay, and for the screw dislocation, you can see its dislocation is right here, right? And we also apply a shear force. I will explain what shear force is later. Okay. And this lattice atom move when the shear force applied from here to here. Okay, and this direction is called the Burgers vector. Okay, it's called the Burgers vector. And for the screw dislocation, the Burgers vector is parallel to dislocation line. Is that clear? Or we can say the Burgers vector is perpendicular to the direction of dislocation movement. Okay, and no matter its edge or screw dislocation, the final results are identical. That means we have extra atomic plane. We're shifted. Okay, and this plane is the and this plane is the closed packet plane, or it's a sleep plane. Okay. Okay, so let's look at the screw dislocation. We just called one atom sig phase, and we apply the shear force. Okay, we apply a shear force, and the atom here will move from the original site to here. From here to here. Okay, so it's the this is the Burgers vector, right? This Burgers vector. And the locus of this screw dislocation, for example, the atom here is its locus is a spiral planar ramp. Okay, it's a spiral. Wow, it's a spiral planar ramp like this to here. Okay, can you imagine that? It's a spiral ramp, planar ramp. That's the reason why we call it screw dislocation. Okay, screw dislocation. Okay, and the same thing for the edge dislocation. We have half plane, extra half plane of atoms right here. Okay, here. Okay, and we apply a shear force. Shear force. Okay, and this half plane will move. Okay, will move depending on the shear force you apply. Okay. Okay. So we just look at the line defect screw and the edge dislocation, right? For edge dislocation, we have extra plane of atoms here, and for the screw dislocation of the locus is a ramp. Okay. Okay, it's a ramp. It's a spiral ramp. Okay, it's a spiral ramp like this. Okay, and this case is only for pure shear force, pure shear stress. Okay, and mostly the materials will be undergo mixed load. Okay, for example, we have a metal rod, and this rod we might apply a torsion, we might apply a bending, we might apply a tension on this metal rod. Okay, so therefore, the dislocation inside this sample will not just edge dislocation or screw dislocation. It must be a mixed dislocation, coexisting. Okay, coexisting. Okay, it's for the edge dislocation. Edge dislocation. Okay, it's for the edge dislocation. Therefore, as what I mentioned, for a materials, for sample, for what like the metal rod, okay, we will apply a tensile, we apply a torsion, we apply a bending stress on this sample. Its dislocation must be mixed. Okay, therefore we have the edge dislocation here, and we have the screw dislocation here. Right? It must be mixed. It must be mixed. You see that? Okay, it's a 3D image of the screw dislocation. Okay, screw dislocation. Okay, so as I mentioned previously, the stress, right? I mentioned the stress is shear stress and normal stress. Okay, so what is normal and what is shear stress? Shear. For normal stress, is that a force applied perpendicular to the area of interest, and for shear force act parallel to the area of interest. Okay, one is perpendicular, and for the shear it is the parallel to the area of interest. Okay, and when the plane contain both dislocation line and the Burgers vector, is known as the slip plane. Okay? Like this, I show you this picture. for this. Okay, for this. Okay, for a plane contain a dislocation line. This is a dislocation line, and this is the Burgos vector. For a plane contain the dislocation line and the Burgos vector is the slip plane. Therefore, the slip plane is what? Where is the slip plane? Here, right? Right, here is the slip. It's this plane. It's the plane I draw it. Okay, this plane is the slip plane or the closed pack plane. It's a slip plane. Okay, that's it's mentioned here. When a plane that contains both dislocation line and Burgos vector is known as the slip plane. Okay, and if a significantly large force is applied parallel to the Burgos vector, that is the slip direction, and dislocations can move in a crystal via a slip process. Okay, therefore we have to figure out what's the force, the shear force, right? The force applied to the force is applied parallel to, right? So that's the shear force. How large is of this shear force to trigger the dislocation occur? Is that clear? Okay. So there's a scientist, it's called Navarro. He defined a stress. Okay, to make the dislocation and this slip process to occur. Okay, so as what I mentioned, that a combination of a slip plane and the slip direction forms a slip system. Okay, slip system. And what's this Navarro stress? Okay, it's a stress required to move a dislocation between equilibrium position. Okay, it's a Navarro stress. Okay, it's an exponential function. Okay, it's an exponential function. Also, it is derived from experiment. It's derived from experiment. Okay, here C and K are constants for different materials. So it's materials dependent. It's material dependent. Okay, and the D is what? The interspacing. The interplane spacing is the D spacing. We already mentioned in the previous chapter that XRD, X-ray diffraction, can figure out what the D spacing is between two adjacent planes, right? Okay, and B is the Burgos vector, magnitude of the Burgos vector. Okay. Okay, so we can measure the D spacing, and we do the experiment, and we figure out the C and the K, the constant, with respect to different types of materials or different types of metals. Okay. So we can observe those dislocations under a scanning electron microscope. Okay, we can clearly, those dislocations can be clearly observed under microscope. Okay, under microscope. Okay, so the vectors determine most likely active slip systems are the slip direction should have high density or small repeat distance. So here, the slip direction should have the high density or a small repeat distance. What's that mean? That means the slip direction is what? The close pack direction, right? Close pack direction. have the higher density, right? Higher density. And the slip plan should have the higher planar density. That means it's the close pack plan. Okay, and these two combination of these two is called the slip system. It's called a slip system. Okay, and dislocations do not easily move in the material with covalent bonds. Well, in other words, we can say that dislocations do not easily move in materials with a strong bonding, in the primary bonding. Okay, not just covalent, ionic. Still, like materials with ionic bonding are also resistant to slip. Okay, because it's strong bonding with two atoms or two ions. It is not easy to shear, to move them apart. It's not easy. Okay. Okay, so as I already mentioned, what is the slip plan in a different crystal structure? And the slip plan is the closed pack, right? Closed pack. Closed pack. Closed pack plan. Right? So for example, the FCC structure. What's the closed pack plan of FCC? What's the closed pack plan of FCC? Let's draw here. For example, we have unicell for FCC structure. Okay, so what's its closed pack plan? It's 111, right? It's this plan. This is a 111 plan. Right? So this plan is 111. So it's closed pack plan. Therefore, it is its slip plan. So when we apply a force, when we apply a tensile force on the FCC metals, the slip process occurs along the 111 surface, 111 plan. Okay, and the direction, the slip direction is what? The slip direction is here, right? Here, 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 here. Therefore, what's the slip direction of FCC structure is what? 110. Sorry, 110, right? Therefore, what I say, the slip plan represents closed pack plan in a crystal structure, and the slip direction represents the closed pack direction in a crystal structure. Okay. Okay, so the significance of the dislocations, as in the previous I already mentioned, when we apply a force, tensile force on the metal rod or metal samples, when this force reached a certain value, a specific strength, it's gonna trigger the slip process, right? Slip process. That means this material start to deform plastically. Okay, therefore, plastic deformation is an irreversible change in shape. In other words, elastic deformation is is reversible. Okay, it's reversible. So what's the deformations of elastic and the plastic deformation? Yeah, reversible and irreversible. So when we apply a tensile force on the metal rod, when the force is released, the force is removed, the dimension will return to its original dimension, and it is called the elastic deformation. If the force is removed and the dimension cannot return to its original dimension, that means the permanent deformation occurs, right? So we can say it is the plastic deformation. Okay, and applying stress causes dislocation, movement, and the cumulative slip of numerous dislocations causes plastic deformation. So now it's have a relation between the slip of numerous dislocation causes the plastic formation. Okay, I remember I already say you can try an experiment. You can use the paper clip. Here's a paper clip. Just make it stretch. Just stretch it to make it straight, and you just keep bending it. Just keep bending this paper clip. What's going to happen? You increase the dislocation inside this paper clip. So you will feel, wow, this paper clip become harder and harder, right? Become harder and harder. And finally, it's going to break. It's going to be broken, right? It's going to be broken. Okay. Okay, so let's look at the other stress, shear stress, to define the dislocation. Previously already mentioned a stress is called the Nabarro's stress, shear stress, right? To define, okay, so what's the shear force to trigger the dislocation? And the other law is called the Schmid's law. Okay, Schmid's law. Okay, so what is Schmid's law? Schmid's law gives the resolved shear stress in the slip direction. Okay, tau R is the resolved shear stress. As already mentioned, what is shear stress? Shear stress is the shear force divided by area. Right? What is normal stress? It's the tensile force divided by the cross-section area. Cross-section area. Okay, so this stress, this resolved shear stress, is different from the barrel stress, because the Schmid's law is derived from the materials, crystal materials. So let's look at this. Let's look at this. When we have a metal rod and we apply a force, right? Just can use any tensile stress machine to apply a force. Okay, and the normal stress equals to force divided by area, and this area is the cross section of the cylinder, A naught. Okay, and this plane is the slip plane, or we can say it's the closed pack plane. Okay, so we assume here is the slip direction, just we assume it. And the angle between the normal force that we apply and the slip direction is called the lambda here. Okay, and the normal to the slip plane is right here. Okay, the normal to the slip plane. And the angle between the normal to slip plane and the normal force we define as a phi. Okay, therefore we can figure out the shear force, right? Shear force from this triangle, is lambda, this angle, right? So we can find the shear force. Is that clear? And also we can find the area of slip plane here from this triangle. Okay, from this triangle. Therefore, the area of slip plane equals to the A naught divided by cosine phi. Okay. Therefore, we can figure out what the shear stress is. The shear stress is what? The shear force divided by the area of slip plane, right? We just substitute this to here and substitute this to here, right? And then we can figure out this called the resolved shear stress. We can figure out this term. Okay. Do you know what I'm saying? Okay. And the critical resolved shear stress is the stress required for slip occur. It's the same concept as that we mentioned before, the Nabarro stress. Okay. Therefore, when the shear stress equals to the critical resolved shear stress, the slip occurs. Okay, the slip occurs. Okay, when the shear stress equals to the critical resolved shear stress, and slip occur. Okay, occurs. Okay, so I'm gonna stop the course here, and I will continue next week for the crystal structure, the slip system. Okay, I will explain more about the influences of the slip system. Okay, and what's the effect of the slip system correlated to the mechanical properties. Okay, so we'll stop here.